So far, we've spent a lot of time studying these kinds of differential equations, linear, homogeneous, constant coefficients. And for this lecture, I want to look at non-homogeneous. So that means x prime equals ax plus possibly some function of t. And this is like the compact way of writing things, but remember that x vector of t, which is what this x vector here is really a package consisting of two or maybe even more functions. And so f vector of t also is like two or more, n functions, where n is the number of unknown functions, also the number of equations here. So this would be called, assuming that the coefficients here are constant, this would be called a linear non-homogeneous. If this is non-zero, then this would be called non-homogeneous differential equation system, still with constant coefficients. So that's what I want to study. And how about a quick reminder as to how this is linear non-homogeneous? If I subtract the ax to the other side and write it like this, then I've got a linear operator being applied to x on the left-hand side. So that linear operator is d dt minus a. That's what's being applied to x. And then on the right-hand side, I've got f, and I want to solve. Solve means find functions x such that when I apply this linear operator to them, we can call this L, f is the output. So in other words, I kind of want to invert L. So you see why this is called non-homogeneous, is because the right-hand side here ends up being non-zero. I cannot just subtract this over, right? You might think like, why don't you just subtract it over, and then you have a zero there, and then you can just call anything homogeneous if you want to, right? You can just force a zero on the right side. Well, you can't do that because if you view this as an operator applied to x, that operator would not be linear. So we're only subtracting this one over because then we can view the left-hand side as linear operator applied to x. So the linearity is important for us to be able to apply the linear algebra ideas that we've been applying. An important one, which still applies, being the following, that if you want the general solution to one of these, so here x could be a column vector of numbers, and f is a number, and L is a matrix, or x could be an unknown function, and f an unknown function, and L is a differential operator. So let's say you want the general solution to this thing, then, like we've said a million times, you can solve the homogeneous version first. So solve this one, and here by solve I mean get the general solution. So let's call that x homogeneous general. So you'll get some general solution, and then somehow find some solution. So just find one, by any means necessary, find one solution to the non-homogeneous. So I wouldn't call that a general solution, that would be a particular solution to the non-homogeneous. Non-homogeneous, particular, and then finally add them. So do, I'll be lazy here and copy, do this plus this. And that will be x, that would be what you wanted, a general solution to the non-homogeneous. So non-homogeneous general. So this just always works as long as your L here is linear, and it works in this situation too. But you remember what the hard part is, right? Right now we have this part locked down, right? solve the eigenvalue problem for your matrix A, this is, in our context, this is x prime equals ax, right? If I don't shove this term to the left-hand side, then the homogeneous is this, x prime equals ax. We have this locked down. Solve the eigenvalue problem for A, and we know how to do this, get the general solution. This one is hard. So this is the full x prime equals ax plus f, which is a vector-valued function of t. So just finding one solution to the non-homogeneous, that is hard. So how did we do that before when we had one unknown function rather than a system of differential equations with several unknown functions? How did we do this before? We had two possible methods that we could use. When the function on the right-hand side is very simple, we can use the method of undetermined coefficients. And that becomes available when the function here is simple enough that you can make a good guess for the method of undetermined coefficients. You can still do that here, and it has the advantage of giving you a nice solution and not being that hard to work out. But it works in a very limited number of cases. Our second method was variation of parameters, which the nice thing about variation of parameters is that as long as you did this, which we can do, we know how to do this, variation of parameters always works to get you one solution to the non-homogeneous part. So variation of parameters always works to get you to the end here, to the sort of holy grail for your differential equation. But there's a disadvantage, which is nasty integrals. Okay, so in this context where you have system of differential equations with several possible unknown functions, those two things are still available. Method of undetermined coefficients and variation of parameters are options that we could explore. I'm going to not explore method of undetermined coefficients because it's honestly not that different. I don't think there's too much more insight that you can gain from learning about it again in this context. I think variation of parameters, which I personally disliked studying, I don't know about you, but I don't really like it that much back when we were doing chapter 2, since there's a lot that seems like it's coming out of nowhere. I mean, it's cool that it gives you something that always works in the end. So I appreciate it for the power, the theoretical power of it, but it's not that fun to derive if there are steps that just seem like they're coming out of left field. In this context, however, you will see that variation of parameters is actually very natural and pleasant to derive. Remember, here, unlike in chapter 2, here we're looking at a first-order situation, which really does simplify things. And before you start thinking, oh, so this is lamer and more limited than what we studied in chapter 2, remember that what we're studying here subsumes what we studied in chapter 2 because those second-order differential equations from chapter 2 can be always converted into first-order systems of differential equations. So, if you want to, you can forget everything you learned from chapter 2 and just remember chapter 4, because that sort of includes everything we did before, as long as you know how to convert a second-order differential equation into a system of first-order differential equations. Okay, so in the next video, let's look at how variation of parameters helps you go from having the green part, which we know how to get this, to giving you a way of getting this red part, a particular non-homogeneous solution.